Hello and welcome to another PyMOL Quickie with me, Dr. Ross. Today we will make mutations in PyMOL using the GUI, the command line, and also put together a bash script. As always, you can expand the description for the video timings and a list of the commands, and also please like and subscribe for new content. Hello and welcome to this video on how to make mutations in PyMOL. Please expand the description below and look at the timings there in order to skip straight to the relevant section that you're interested in looking at. But I thought first of all, before we get into the nitty-gritty, I'd give you a quick introduction into what mutations are and why we might want to make them and the PyMOL environment. So hopefully you know that your protein structures are made out of amino acids, and there are 20 naturally occurring amino acids. And for example, here you can see that I've grouped some of those 20 amino acids into their various different biochemical states. For example, at the top here we have small hydrophobic, larger hydrophobic, the polar hydrogen bonding residues, the positively charged residues, and the negatively charged residues. We have here glycine, alanine, valine, cysteine, proline as the small hydrophobics. We have leucine, isoleucine, methionine, that's the sulfur there, sorry, bad colouring, tryptophan and phenylalanine. We have serine, threonine, tyrosine, asparagine, glutamine as our polar residues. Then our positively charged residues, we have a lysine, we have arginine, and we have histidine. And for our negatively charged residues, we have aspartate and we have glutamate. Now, of course, positively charged, negatively charged, polar, small hydrophobic, large hydrophobic are very different biochemical properties that they have. For example, tryptophan can initiate hydrogen bond interactions as well. Our cysteine can make disulfide bonds if it's appropriately formed. A combination of a positive and a negative can make a salt bridge, and of course our polar groups here can interact with waters, and our hydrophobic groups can make the hydrophobic core of the protein. Also, different amino acid side chains are responsible in catalytic triads in enzymes. So if we want to make changes to our protein structure in a biochemically relevant way, then changing the constituent of the amino acids and in relative positions is something that we want to do. And of course we can model this in PyMOL. Now PyMOL is not a sophisticated modeling environment which uses complicated force fields in order to make models that are of the best accuracy for today's purposes. There are plenty of bits of software out there that can make much better predictions of what will happen when you introduce a mutation than PyMOL. But PyMOL is a nice user-friendly environment, and you can make, and it's very good for making presentations or making thought exercises when you're making mutations. You can use PyMOL also to generate mutant structures, which you can then feed into some secondary program in order to relax those structures into more appropriate conformations. So that's really my quick introduction. I should talk a little bit about Rotamers as well. Let's try that on this valine here. So when you first start using the mutation wizard and you click on a residue and you say no change, what it does is it gives you down at the bottom in the state control here different rotameric states, and we can cycle through those rotameric states by clicking through the play button. And you can see that there's one rotameric state corresponding to the state that we initially had. There's another rotameric state which is a 120 degree rotation of that, and there's another rotameric state at 240 degrees rotation. And of course, we can go back to our first rotameric state at then 360 degrees rotation. So why is that? What we can do is look down at this covalent bond here, and we can see that the position of our hydrogens on this atom here are staggered compared to the positions of the covalent bonds which represent the position of the hydrogens on the atom to which it's joined. So as we move through our rotameric states, the reason that we're moving in these 120 degrees is because we are looking at positions by which we can keep that staggering occurring between the hydrogens on this atom and the hydrogens on the atom that it's covalently bound to. And the reason for that is because you get clashing between these atoms here and here, and therefore really we have 3 choices per bond, and therefore as we look at more complicated amino acids such as this guy here, we're limited to the amount of different rotameric states or optimal positions that amino acid can take, and PyMOL allows you to sample those and will pick the best one for you. But anyway, on with the rest of the tutorial. Hello and welcome to the first part here of the Making Mutations PyMOL Quickie. Here we're going to be looking at the GUI, but of course, as ever, the first thing that we need to do is to fetch our PDB. So here we're going to be using the crystal structure of a topoisomerase 1 from Leishmania donovani, and so in order to bring this in, we're going to fetch 2B9S, and here you can see we have our protein here wrapped around this double helix of DNA. Now, as usual, we're going to use a few commands here just before we start in order to make the visual look a little bit more pleasing to the eye. You can see here I've made a specific mention for the polymer.nucleic acid section that we want to show that as sticks, and the rest of it you might be familiar with. And there we go, now we can just see that everything looks a little easier. So we want to make a mutation. How do we go about doing that in the GUI? Well, what we're going to use is the wizard, which you'll find up in the toolbar, and you can see here how we navigate through the toolbar. We'll go to wizard, we'll go to mutagenesis, and then we'll go to protein. Now you'll also see that we've got mutagenesis for nucleic acids, which is why I brought in a structure here with the nucleic acid component as well. But we'll just go through the process for the wizard with the protein. Now as soon as I've clicked this, you can see down the bottom right here I've got a whole section of buttons available to me, and in the top left of the screen you can see that it's asking me to do something here. It says pick a residue. So let's go and pick a residue. Here's a residue here, an arginine, and that seems to be an interesting residue, as maybe it's making some interactions here with our nucleic acid. So there we go, we can see our arginine here, and you can see it says pick a residue, so we will click on our arginine, and now you can see that we get this white kind of ghost residue here, which is showing how PyMOL would prefer to orient that particular sidechain. And what I should also do is just bring your attention down to the states at the bottom, and you can see that we are on state 13 of 20. Now those states refer to the rotamers available for the particular amino acid. Arginine has 20 rotamers and we're on rotamer number 13. And we can use the state control buttons here to play backwards and forwards through those different states and watch and see where we get clashes and interactions. You can see that maybe this looks like a nice place for it to be, as it's kind of interacting with a lot of potential hydrogen bonds there, but there are some clashes too. State number 13, which it gave us, I think is the state in which there are the least amount of clashes. These clashes being highlighted by these kind of red cylinders. So what we'll do is we'll head back down to state 13, the recommended rotamer. You can see that the recommended rotamer is actually a little bit different from the natural rotamer as well. So we've picked a residue, And what we could do is, without making a mutation at all, we could just change the rotameric state using those state controls there, and then we can say apply, and it will give us those new rotameric positions that we want. So we can pick on the no mutation button, and we get here then a list of our amino acids, and you can see that our charged amino acids here have more than one state in order for the different protonation states of the charged residues. However, we can pick a particular residue that we like, and now you can see our ghost residue here has now been mutated, that particular different residue. And again, down at the bottom we now have our states here, 13, so there's 13 of 13 states here, and we can cycle through our different rotameric states for that particular amino acid as well. It's probably reasonable to stay on the recommended one that PyMOL initially gives you, as that should be the least clashing residue. So when you're happy with it, we can just click the apply button and move on to the next amino acid that we want to mutate. What we can do, instead of looking through the structure for amino acids that we want to mutate, we can click on the sequence view, and up at the top here we can, for example, say if it's going to be residue 151 that we want to mutate, we can click on that, and you can see that by clicking on it on the sequence view, we've already highlighted it for mutation in the wizard. And then we can say that maybe we want this to be a phenylalanine, for example, with a particular slightly different rotamer. And then we can say apply. Now you can see that there are other buttons apart from the mutate. This allows us to put on different N or C terminal caps onto our mutated residues, presumably if they're on the N or the C termini. We can add hydrogens or remove hydrogens, or keep the current hydrogens, which at the moment hydrogens are not shown. We can show lines or sticks for our mutated residues, and we can have backbone dependent rotamers or backbone independent rotamers, so therefore the rotamers that you get are dependent on I guess the secondary structure. But when we're happy, we can say apply, as we've done to apply these mutations, and then we can just hit the done button in order to close the wizard, and our mutations are here. Now what we should do once we've made a mutation is to relax our structure. Let's just see if we can. I believe that this is the place here where we introduced an arginine, asparagine here in the place of an arginine. So what we should do in order to relax the structure is to use the PyMOL inbuilt sculpting program, and that's under the build menu. So once you've made your mutation, into build, so build, sculpting, and then sculpting to turn the sculpting module on. And once the sculpting module is on, we can activate it, and you can see that now we've made some relaxations, and then that happens pretty quickly, so we should deactivate it shortly after activating it, and then turn the module off. So sculpting on, activate, deactivate, sculpting off, and what that will do is it will just make sure that all of the atoms are positioned away from each other. What can happen quite often is if you make a mutation and there's a small and the atoms are too close together, that you save your PDB file and then you can reopen it, and PyMOL will automatically put a new bond between those atoms, because the way that PyMOL draws the bonds in the program is purely by distance. So if you have two atoms that are within covalent bond distance but are not actually covalently bonded in reality, PyMOL will just draw in a bond there. So the sculpting algorithm there helps to move non-bonded atoms away from each other to such a degree that they're outside of the covalent bonding range for PyMOL. And there we are, as simple as that. That's how we do it in the wizard. Again, there's a wizard for the nucleic acids, and maybe we'll just have a quick demonstration of that. I must say I've never used this before. Nucleic acid, pick a nucleic acid, this guy, and there we go. And we have we can even choose a uracil for some RNA if desired. And there we go, we can also see that we get this kind of ghost molecule until we apply. So there we go. Okay, that's how to use the GUI. Coming up next, how to use the command line. Okay, so we talked about how to mutate in the GUI. This is how we're going to mutate in the command line. So we'll start off by fetching in our crystal structure again, and this is the topoisomerase that we had previously. And what we'll do is, just to help guide our eyes, we'll make that into something which is nicer to view with respect to the amino acids, so that we can look at the positions. So first of all, there are not inbuilt PyMOL commands specifically for making the mutations that we want to do. So what we need to do is use the Python API for PyMOL, and that is done by using these cmd dot commands here. So basically this is asking Python to do the work for us rather than PyMOL, which is of course built on Python. However, anyway, so we can just copy these as we would normally into PyMOL, and you can see that what we've done here is that we've just turned on our wizard without going into our toolbar here, and we can see that it wants us to pick a residue, and it's opened up our box down at the bottom. Now what we can do is we can select that we want to mutate to a phenylalanine here. It's already on a phenylalanine, but let me just show you that if we change this to ALA, you can see that we've changed our residue that we're mutating down to ALA. So really what we're doing with these commands is we're just manipulating the wizard. And then we can say, instead of clicking on the particular residue that we want, we can say, well, actually we want to pick residue, this is chain A 352, and you can see it centers in on that residue there, and it makes our mutation here. And then we can say, well, what you can also do, of course, is to select which rotamer you want. But of course, it's very hard to do that, to know what rotamer you want when you're using the command line to do this. It's much more intuitive to use a visual method and to use the GUI as it's been designed in order to choose your rotamer. So this is kind of redundant when you're using the command line, and PyMOL will pick the best rotamer for the position that it's currently in and present that, and that's probably the best one to keep with. So although you can use this, there's probably no need to actually do it. So then what we can do is we can just apply the mutation from the wizard, and then, as you saw previously in the GUI version, what we'd like to do is to go into the build menu and use the sculpting that we used before. However, we can use a bunch of standard PyMOL commands rather than the Python API here in order to do our sculpting for us. So what we'll do is, I'll just talk you through this very quickly, is that we'll select our mutant residue, which is this guy here, chain A residue 352, and we'll call that mutant. So we're going to make a new selection called mutant, and there we are. You can see here is our mutant residue. Now we're going to select a new selection. Very inspirationally, I've just called that selection new, which you could call whatever you like. But what we're going to do here is we're going to select all residues by the residues that are more than 10 angstroms away from our mutant residue. So you can see what we've done here is we've selected all of these guys in the outside, but we've left a little shell of 10 angstroms around our mutated residue. Then what we'll do is, now that we know that we can select that, we're going to use flag fix. And what flag fix does is it means that it makes these residues here rigid when we use our sculpting that you saw previously. Then we can activate our sculpting, iterate 2000 cycles of the sculpting, and then close and then stop sculpting. And so if we do this, what you'll see is that the residues on the outside will remain in fixed positions, whereas the residues within this 10 angstrom shell around our mutant will have made some slight changes, which we shall hopefully see in a moment. There we go. So a slight relaxation in the center here, and everything else has remained fixed. And that's cool. And now we can just we can save our molecule, and of course we'd just do that by going to File, Export Molecule, Save, and then maybe we'll choose a PDB in order to save that. And there we go, making mutations in the command line. Now of course the benefit with the command line is that you can quite easily just change what you want to mutate to, and you can quite easily just change the residue which you're mutating. And then let's just actually do a quick example of that. Let's say that actually it's going to be residue chain A, residue 150, and we're going to change that to a histidine. Why not? So we'll change that to A150 as well. And so, because it's all on the command line, we'll remove our Rotamer selection there. What we can do is start from scratch, copy everything in. Now it won't make a new display until after it's done the relaxation. But there we go. So there's our histidine that we've just introduced there, with a relaxation around it. Now it just so happens that the area in which that histidine has been introduced is in this polyala area. Presumably the side chains weren't able to be resolved there in the crystal structure. But anyway, there we go. So that's a nice quick and easy way of making mutations. Next up, we'll put this script that we've just made here, or we'll put these commands that we've just made into a quick script, and we'll make hundreds of mutations in a few minutes. Alright. So we've seen how to use a GUI, and we've seen how to use the command line in order to make mutations. What happens if we've got loads of mutations that we want to make? Well, what we can do is we can throw the commands that we went through in the last section into a script file, and we can run those commands and make a whole bunch of different mutant structures. What you can do if you're skilled with Python scripting, or if you know what you're doing, or if you have a good Google, is that you can actually call PyMOL within Python. So rather than calling Python within PyMOL, which is what I was doing in order to use this wizard, you can just call PyMOL within your Python environment. And of course there's no GUI, it just does the stuff behind the scenes for you. And essentially that's what we're going to have happen here as well. So let's just quickly go through my way of doing this. This is probably not the best way at all, but if I want to go and make a bunch of mutations, this is the kind of way that I might go and do it. So first of all, we need to think about why we're going to be making mutations. So I'm just making up a little bit of a reason here. Here's my let's bring back our protein structure. So we'll start our session again. Here's our topoisomerase. Maybe we're interested in mutating the residues that bind to the DNA. That would be a sensible investigation to make. So what we can do here is we can start off by making a selection. We're going to select by residue all the atoms that are part of the protein chain that are within 5 angstroms of the nucleic acid chain. So if we do this, you can see that now our highlighted selection here is just the residues that are within contact distance of our nucleic acid. And what I'm going to do now is I'm going to save that as a PDB file called interaction or interact.pdb. Okay, so that's saved. Now I'm in a Windows environment here, but I'm using the bash for the bash subsystem for Windows, and that allows us to have an integrated bash terminal in our Windows environment. So we can see here that I have my interact.pdb here. So we can use a few bash commands here. So for example, what I'm going to do here, and this is why you should never learn bash, because look at this command here, look, it's literally just slashes. But anyway, Going to use this bit of grep here. What we can do is we can grep out the carbon alphas from our PDB structure. So this is all of our carbon alphas from our interact. So this is only the interacting carbon alphas. Then we can cut residue, cut character 22 to 27 from that. Whoa, stop doing that. That was wrong. We can cut character 22 to 27 from that. And that now just gives us a list of the chain and the residue number. And then we can replace the spaces that we have in there for slashes. And that gives us now a PyMOL based way of defining our chain and our residue. And so we'll do that command and we'll stick it into something called residue list. Now we're going to make a loop for each of our entries into our residue list, just to save a bit of time, because otherwise it'd be very boring. I'm actually just going to crop that, so we're going to look at the top 5 residues there. And then we're going to have our mutant residues, which are going to be either an alanine and let's just say a lysine. So this would be essentially doing an alanine scan and a lysine scan across all of the residues that contact our DNA. And then we'll quickly make a couple of variables here where we can define the chain and we can define the residue number based on this here. And then we're going to echo what we're doing to the terminal so that we know what's happening. And then we're just going to recreate our PyMOL commands here. So this is, we're just echoing out all of our PyMOL commands that we've previously been through into a file called mutate.pml. Then we'll run PyMOL. When you're running PyMOL by the command line, you can use this -qc in order to make it quiet and no GUI, and therefore it won't fill the terminal full of too much stuff, although it does give you plenty of output. And of course it won't open up the user environment either. And because there is actually a fair bit of output, I've just sent that off to DevNull as well. If you're using the Bash for Windows environment, it's useful just to put in a little comment like this here, which tells PyMOL to stay open until you find your output file that you're looking for. Otherwise, it can start turning over before it's completed its task. You won't get that problem if you're working in Linux or on a Mac. It's only for the Windows subsystem that you get that. So, of course, what we can do is we can stick all of that into a file. So this is just really a direct copy of that. What we should do actually is we'll just make it so that we're doing this alanine and lysine scan. There we go. And now it's just really, you can see that inside our folder here, we've only got those initial PDBs, and we can just run our little make mutant script here, and you can see that it's talking to us now, making residue 41 lysine, 42 alanine, 42 lysine, and so on. So this is going through the process here. It's at least reporting to us that it's making these mutations, but of course we've only asked it to report here. And so when that finishes, this is why we're only going to do 5 of them. There we go. We can see that now we have all of these PDB files here. And what we can do is have a look in PyMOL at star.pdb, open all those guys up. And okay, so what we can do is we can open up our sequence view here, and we can see that we have our different objects loaded in here, our PDBs loaded in as different objects, and we can see that we're going to start off, our top line here is 142, so there's 142 alanine, and then 41 alanine, and then 42 alanine, 45 alanine, and 93. alanine. And you can see that we've made these alanine mutations here, and they don't correspond to the wild type there. And of course that's going to be the same for the lysines as well. And of course what we can do is middle click on these guys, say as sticks, so that we can see the mutations. And you can see that if we 142, this guy here, we can see that here it's an alanine, whereas in the other structures it's a lysine. And again, if we go and turn on 41, and we look at 41 over here, it's an alanine. And of course, if we look at one of the other structures, it was a different residue. So there we go. Very quick script that you should be able to copy and paste this into any kind of Unix-based environment, and providing you've given it your residue list and some amino acids that you want to change it to, you can generate a whole bunch of different mutant structures there to do with whatever you want. Alright, thanks very much. Thanks very much for watching. Hope that was useful. Please see the longer tutorials which I've put together and are available. Tutorial number 1 and tutorial number 2 are very good. And of course, like and subscribe for more content. See you next time.